Hi, I'm Brian, and in this video we're going to review electric potential energy. In order to do that, we'll first explore potential energy fields. Then we'll compare like charges and unlike charges and see how their characteristics differ for electric potential energy. By the end of this video, we want to be able to predict the energy contained within any given arrangement of charges. In doing this, we'll need to pay special attention to the signs of those charges for whether or not we wind up with a positive or a negative energy. And we'll want to understand that by the end of this video, as that is the most confusing part about electric potential energy. This will allow us to answer questions like the one at the bottom of your screen regarding alpha decay of a californium nucleus, paying attention to the energy change of that system. First things first, we want to understand electric potential energy in relation to potential energy in general. Potential energy means that we have some conservative force that results in being able to store that energy. When you push against a conservative force, it stores energy, and that energy will then come back out and be transformed from that potential energy back into kinetic energy. Two other examples of conservative forces and the potential energy that go along with them are gravitational potential energy, resulting from the force of gravity, and elastic potential energy, resulting from the elastic force. In these cases, energy is stored in certain system configurations and then can be released later. This can be seen when a ball that has high potential energy rolls down a hill, or a stretched spring will return to rest position. In both of these instances, these are spontaneous changes, as the system is going to a lower energy state. Energy is going from being stored as potential energy and transferring into kinetic energy that can leave the system. Just like gravitational and elastic potential energy, electric potential energy follows the same principles. Spontaneous changes happen as we have charges moving in the direction that the electrostatic force causes them to move. In this specific situation, we have a negative charge and a positive charge separate from one another by some distance. The electrostatic force between them is a force of attraction in this case, so spontaneous movement will occur when that negative charge is released, and it will accelerate towards the positive charge. This causes a decrease in potential energy of that system, and the potential energy of the system can be calculated using U equals KQQ over R. Electric potential energy is just like any other type of energy. They can be converted back and forth, and in fact, many other types of energy with which we're familiar are actually just applications of electric potential energy. As such, like all energies, the unit of electric potential energy is the joule. And on the previous slide, we saw the equation for calculating electric potential energy. In this equation, the K is Coulomb's constant, a constant very similar to the gravitational constant in the law of universal gravitation, equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. The big Q is the source charge magnitude, as often electric potential energy will be given as a relationship between a source charge, like a nucleus, and a charge that is being affected, like an electron or perhaps a positron. The little q is the charge of that point charge, and the r is the distance separating those two charges. This equation should look fairly similar to Coulomb's law, which states that the electrostatic force is equal to kqq over r squared. The only difference here is that r is not squared in the denominator of the electric potential energy equation. That is because our electric potential energy equation is actually force times distance. When we take the electrostatic force as calculated by Coulomb's law and multiply it by the distance you have to move the charges apart, which is the same as r, the r and the d cancel, leaving us with just one r in the denominator of the energy equation. In the numerator, we do want to pay special attention to whether those two charges are positive or negative, as sign does matter in this equation, and we'll be taking a look at that in the next two slides. Before we look specifically at that though, let's think a little bit about how this equation is applied. First, how does the potential energy change when separation doubles? When the separation doubles, that means we're doubling the denominator. So we now have 2r in the denominator, so we would decrease that potential energy by a half. On the other hand, let's evaluate how the distance would have to change in order for the potential energy to double. In order to get the potential energy to double by changing the radius, which is in the denominator, you have to divide by 1/2. So you have to have 1/2 in the denominator. So we go to half of the radius, resulting in twice as much potential energy. As we look at electric potential energy, there are only really two possible situations. In the first situation we'll evaluate, we're looking at like charges. When we have like charges, we either have a positive and a positive, or a negative and a negative being plugged in for big Q and little q. This means that no matter what, the result is a product that is positive, because a positive times a positive is a positive, and a negative times a negative, still a positive. And since the product of the two charges is positive, the potential energy must also be positive. If we apply the electric potential energy equation to this means that as we increase the R, that energy gets closer and closer to zero. This should make sense, as like charges that are farther and farther away from each other are happier and at a lower energy state. They're not pushing each other away. They are where they want to be. This can be seen in the graph at the right, where at low R there is a high potential energy. Then as the force pushes the charges apart, they get farther and farther away, increasing the R, causing the energy to go down, converting it into kinetic energy. The thing in common in this situation, as we have like charges, is that like charges always repel. If we have two positive charges, they will repel one another. If we have two negative charges, they will also repel one another. So as we have repulsive forces, they're trying to lower the potential energy back down towards zero by pushing those two charges apart. The converse situation is to have unlike charges. When we have unlike charges, one of the Q's is positive and the other is negative. This means we will always have a product that is negative, and therefore we will always have a potential energy that is also negative. The result of this is that to decrease energy, R must also decrease. This is because those opposite charges are at their lowest energy state when they're closest together, and as you move them apart, they reach a higher and higher energy state that gets closer and closer to zero. This is shown in the bottom portion of the graph at right, where we see that the highest energy of the unlike charge line occurs at the highest R value, and then as the force causes the charges to move closer to one another, decreasing the R, the energy value also lowers along the y-axis. The root cause behind this is because those unlike charges will always attract. They like to be near one another. And those attractive forces are working to lower the potential energy down toward negative infinity. And this is what most commonly intimidates MCAT students about electric potential energy. The concept of a negative electric potential energy can be disconcerting. But it's not special, it's not unusual. It's all about a frame of reference. Here we are setting 0 as a specific frame of reference where like charges are always positive and unlike charges are always negative. What we'll be looking at in problems will typically be a change in potential energy, and going up or down is the same no matter which graph you're using. Now let's take a moment to practice by calculating the answer to question number 1. The correct answer is C. Here we are asked what the final electric potential energy of charge Q is, and changes in potential energy are state functions. That means we can calculate each change individually and add them together, and that will give us the final total change. Running through the math of beginning with 100, losing 200, losing 50, gaining 175, and gaining 200, the end result is 225 joules. Now let's evaluate that question we saw at the beginning on our learning goals slide. Go ahead and choose an answer. The correct answer is B. As this is a question about the electric potential energy of an ion, we should evaluate what that energy will be. Plugging into the electric potential energy equation, we have a positive nucleus interacting with a positive alpha particle. And since this alpha particle was emitted from the californium nucleus, that means the R is increasing. Plugging those like charges in, we already know that that means the potential energy will be positive, as like charges always are. And since that emitted alpha particle is leaving, it starts with a low R, which would mean a high potential energy. But then it moves away, increasing the R and decreasing the potential energy. This means overall we will have positive decreasing energy, just as we saw in our like charges graph, where we have positive and positive or negative and negative charges near each other. Here we have a positive nucleus near a positive alpha particle. So we get positive energy that is decreasing as the force pushes them away. Now evaluate question number 3. The correct answer to 3 is D. One piece of information that helps is to remember that when we're talking about energy of particles, we're for the most part talking about the electrostatic potential energy of those particles. So as we compare the aluminum oxide to the sodium chloride and the calcium oxide we've been given, we should look at each one in the context of electric potential energy. Sodium chloride, with a positive 1 sodium and a negative 1 chloride, has two equal and opposite Q values of 1 and negative 1. Calcium oxide, on the other hand, has a positive 2 and a negative 2. So if you would plug that into the electric potential energy equation, you wind up with 2's in the numerator instead of 1's, resulting in a more negative value in the amount of potential energy. Were we to plug in the aluminums and the oxides from aluminum oxide, we have a positive 3 and a negative 2, meaning we will have a value that is even more negative than calcium oxide's value. The only viable answer choice then, the only one that is more negative than 4,000, is D. And finally, let's take a look at question number 4. Go ahead and choose your answer. The correct answer is D. Each of the other three, electron affinity, ionization energy, and bond enthalpy, are in fact measures of how electric potential energy changes as we move electrons around in relation to nuclei. In all three of these cases, we have a positive nucleus interacting with negative electrons. This means we have a force of attraction between the two. In electron affinity, we're talking about how much energy is released when those electrons go towards the positive nucleus, forming an anion. Ionization energy is the energy required to pull the electron away from the positive nucleus, creating a cation. And bond enthalpy is the energy required to break a bond, which removes electrons from that positive nucleus in a bond. In all, for electric potential energy, there are just a few key things we want to know in order to be able to answer the questions correctly. First, keep in mind that electric potential energy is just like any other potential energy, meaning that there is a force trying to cause movement to a lower energy state. We can calculate the total energy change using the equation U equals KQQ over R. And this should look very much like Coulomb's law, but one of the R's has canceled because potential energy is force times distance. So we take the force calculated by Coulomb's law times distance, and the R in the denominator cancels out. Then there are two different situations that can result as we quantify the energy in a system. In either of these situations, we're looking at charges being exposed to an external electric field. Those two possible situations were to have like charges, in which case we always get a positive result, or we have unlike charges, in which case we always get a negative result. In both situations, the forces are acting to decrease the potential energy of the system. And in both situations, we have the largest magnitude of potential energy at the smallest separation. However, this means that for like charges, we have the highest potential energy for the smallest separation, and for unlike charges, we have the lowest energy for the smallest separation. Thank you for joining me on this adventure through electric potential energy, and I wish you the best of luck on the MCAT.